Swayam Prabha. Digital India. Educated India.
In the last lecture we have seen the McCormack scheme for compressible flow, which consisted of a predictor step and a corrector step, which enables us to go from uij n to uij n plus 1. In this we have noted that this can be used for the coupled equations describing the fluid flow, and we also noted that each of these predictor and corrector steps is explicit calculation, and also that it is both second order accurate in both time and space. And so it is order of accuracy is delta t square, delta x square and delta y square, that is not mentioned here. And this enables us to solve for rho, rho u, rho v and et, from which we can evaluate rho u, v and internal energy, from which we get, using the equation of state, we get the pressure and temperature. Now, because this is an explicit method, it has stability limits, potentially stability limits, and when you have these coupled equations and when you have nonlinear equations, all these complications, when these complications arise, it is not possible to get an exact analytical expression for stability, and so McCormack have estimated the stability and expressed this time step delta t that can be taken in using a factor of safety f. So this is delta t must be less than f times delta t CFL. So CFL is obviously the Courant-Friedrichs-Lewis limit, and that is true for an inviscid fluid. Okay, that was what we had, dou u by dou t plus c dou u by dou x equal to 0, no diffusion term. So that is an inviscid fluid. So delta CFL is the inviscid limit, which is given by delta t must be less than u by delta x plus v by delta y plus a times 1 by delta x square plus 1 by delta y square square root. So this is where a is the speed of sound, and this is the two-dimensional form of the inviscid CFL limit. So it is a two-dimensional compressible form of the CFL limit is what this is, and it does not include viscosity effects, and therefore they suggested that it is the delta t that is possible is the delta t divided by 1 plus 2 divided by mesh Reynolds number, and where the mesh Reynolds number is defined as u delta x by nu or v delta y by nu, whichever is the minimum is the one that is to be taken. So let us examine this, limit to understand what it is showing. It is saying that the delta t that you can take has an upper limit, it has to be less than some value, and what is that value? In the case of inviscid flow, 1D flow, this is where the delta t must be less than the Courant number of equal to 1. Okay. So the delta t given by the inviscid Courant number limit is one condition. And that value is not really correct, because what we are dealing with are equations which include viscous stresses. So there must be a modification, and here they are dividing by 1 plus some quantity here, which is a positive quantity, and because it is a positive quantity, it is 1 plus something, so that reduces the delta t that is allowable here. So the fact that you are dealing with viscous stresses reduces the delta t to less than what is possible with inviscid condition. Now with this inviscid condition itself, we put Courant number equal to 1 for the 1D case, and here we have a 2D case, and for a 2D case delta t is not just must be less than u by delta x, it is U by delta x plus V by delta y. Now, for a case with compressible flow, which is what we are dealing with here, there is a speed of sound which also comes into picture. So, this is U by delta x plus V by delta y plus A, which is also a speed. So, it is equal to this, and we need to have a length scale. In this case, it is delta y because it is V and delta x because of this, and here you are taking square root of 1 by delta x square plus 1 by delta y square. Okay. So, all of this together fixes the delta t for the inviscid CFL limit, and this value, the delta t that is possible for the viscous fluid flow thing, must be less than this value by a factor of safety which is 0.9. So, that means that there is at least 10% margin is here, and in addition to that it is decreased by this much. And what is this RE here? That is a mesh Reynolds number. Reynolds number has a velocity scale, length scale, and the kinematic viscosity here. So, here you have two velocities U and V, which one to take? So, you evaluate the Reynolds number for the two cases, taking the mesh dimension delta x delta y as the length equal to the length dimension. So, it is called a mesh Reynolds number. So, this is U delta x divided by nu, the kinematic viscosity, is one Reynolds number, and another estimate of Reynolds number is V delta y by nu. Whichever is the minimum you take here, and you take the minimum because you are dividing by RE, and that makes it conservative. So, if Reynolds number, for example, this is 5 and this is 10 here, you take the minimum, you take 5 here, and so 2 by 5 is 0.4. So, this is 1.4. So, you divide the inviscid limit by 1.4, and then you get the allowable value. So, it is, if this is say 10 to the power minus 3 seconds, so 0.9 times 10 to the power minus 3 divided by 1.4. So, you are getting some factor of safety here and some factor of safety here. Together you are modulating, you are modifying the inviscid limit for the viscous limit, viscous compressible limit is being evaluated in this way. So, this is an estimated stability limit, and if you are within that, McCormack has found that it gives us a stable solution. Now, this has a specific feature here, which means that firstly that there is an upper limit, which means that you cannot have too large a value of delta t, and you cannot have any arbitrary value of delta t. So, it may require, if conditions are such that your delta t is very small, then you have to compute for so many times before you can get up to a target time. Okay. And the delta t here depends both on u and v, it depends on delta x and delta y, and it also depends on the speed of sound. So, if the speed of sound is very large, then the delta t becomes small, because this is delta t must be less than u by delta x to the whole inverse. So, it is equal to delta x by u in a way. Okay. So, that means that as u increases, delta t will decrease. So, in the case where you have large speed of sound, the allowable delta t, CFL itself is limited, and the actual delta t that is limited for the viscous coupled solution is less than the CFL limit. So, as the speed of sound increases, as the flow becomes more and more incompressible, the allowable delta t decreases, and it can also decrease if your delta y is small or delta x is small. So, for example, when you have high speed flows, then you have boundary layer formation. So, in the boundary layer is very thin, so you need to have small delta y. When you make your delta y small, then delta t CFL will decrease, and that will mean that your allowable delta t decreases. So, there are certain restrictions, limitations of the McCormack scheme. It has, first of all, it has being explicit, and like the conventional FTCS, FTBS kind of things, it has an upper limit. It has something like an effective Courant number limitation, and that Courant number limitation is crucially dependent on delta y and delta x, and it is also dependent on the speed of sound. So, there are definitely conditions in which this particular method will have too low a value of delta t and improvements are needed, and one such improvement is the beam warming method. And when we look at eliminating this delta t, we would like to go from explicit to implicit, and so we are going to look as an extra example, as a different method, implicit beam warming schemes. It is not a single method, there are variants here, and it is an implicit method. So, one could expect to have no stability condition, but in actual case we have coupled equations, and when we say coupled equations, we are saying that when we are solving for u, we need to know v, and we are making some estimate of v. It is not the exact estimate, and if you take two large time steps and in the process v is changing, then you could be wrong in the kind of values that you choose. So, even if you have an implicit scheme, you may need to restrict the time limit to some values. So, that is something, but implicit scheme will be better than an explicit scheme in terms of stability limit. So, that is what we are trying to do here. We are looking at an alternative to the explicit McCormack scheme. There is also an implicit McCormack scheme, but we would like to examine this implicit beam warming method, which has also proved to be a successful method and which employs a different way of taking account of nonlinearity, which enables us to get around this limitation of delta t arising in boundary layer type of calculations where delta y is small. So, in this part of the lecture, we will look at the application of the implicit beam warming method or the derivation of the implicit beam warming method for the simple one dimensional case. And so, we are looking at a one dimensional wave equation type of thing, dou u by dou t plus dou f by dou x equal to 0, where f is u square by 2, it is a usual thing, and we have put it like in the previous cases in terms of the E and F's. In the same way we have put this particular equation. Now, the idea is that we want to have a second order accurate implicit method. We already have a second order accurate explicit method, that is the McCormack scheme. So, we would like to improve on it. So, we cannot sacrifice the second order accuracy that is implied in the McCormack thing. So, we would like to do better than that by going for an implicit method. So, the beam warming method is a certain way of deriving a second order accurate implicit method, and we first expand uin plus 1 around uin. So, we write this as uin plus 1 equal to uin plus delta t by delta t times dou u by dou t at in plus delta t square by 2 factorial dou square u by dou t square in plus terms of the order of delta t cubed. So, that is pretty straightforward. And here the derivation is such that you are expanding uin about in plus 1. So, this is something unusual, but I would like you to note that in this case the derivatives are evaluated at in. So, this is expansion about point I comma n or x comma t, and this is expansion about I comma n plus 1. So, x comma t plus delta t. Okay. So, that is the expansion of uin as uin. So, the uin plus 1. So, you have minus delta t dou u by dou t, but it is evaluated at n plus 1 minus it should be plus delta t square by factorial 2 dou square u by dou t square in plus 1 and so on plus terms of the order of delta t cubed. So, nothing different here, okay, nothing new here except the fact that this is expansion about in plus 1 and this is expansion about in. And so, now you subtract this from this and what will you get? You get uin plus 1 minus uin and you have equal to uin, they do not cancel out. In fact, this goes that side, and then that becomes 2 UIN. So, once you do the sums, you will see that UIN plus 1 is equal to UIN plus half of delta t times dou u by dou t IN, which is coming from here, plus dou u by dou t at IN plus 1, which is coming from here. Because you are subtracting, this minus becomes 0, and so you have plus here. So, it is a mistake here. So, when you put plus here and then you delete, you subtract the 2, you subtract this from this, they do not cancel out, because this is dou square u by dou t square at IN, and this is dou square u by dou t square at IN plus 1. If this is also at n, then you can cancel out the 2, because this is at IN plus 1, they do not cancel out, and so you have half of delta t square by factorial 2 dou square u by dou t square at IN minus dou square u by dou t square at IN plus 1. And so, we can write UIN equal to UIN half of delta t times dou u by dou t at IN plus dou u by dou t at IN plus 1, and this can be written as dou by dou t of dou u by dou t times delta t. So, that becomes a delta t cube term. So, this we can neglect this and say that we are neglecting terms of the order of delta t cubed. So, this expression here is third order accurate as of now here. Now, we know that dou u by dou t is equal to dou f by plus dou f by dou x equal to 0. So, we can say dou u by dou t equal to minus dou f by dou x. So, we can substitute that here. So, we have dou u by dou t at I comma n, and that can be written as minus dou f by dou x at I comma n, and here you have dou u by dou t at I comma n plus 1. So, you can write this as minus dou f by dou x at I comma n plus 1. So, we are making use of this equation here to convert these expressed in terms of time derivatives at I n plus 1 and all that in terms of the fluxes that are coming here, and this is a final expression. Now, when you bring the delta t here, then this becomes a second order accurate expression here. Okay. So, now the fluxes, this f is actually u square by 2. So, it is a nonlinear thing. So, there is, we need to make it linear, we need to linearize it, and so we write f n plus 1 that is coming here, or f n that is coming here, as f n plus 1 equal to f n. The space index does not matter here, it is valid for all the things. So, we can write this as, because n plus 1 and n here, we can write this as dou f by dou t times delta t plus terms of the order of delta t square. So, this is f n, and f is a function of u. For example, we said f is u square by 2. Okay. So, we can write this dou f by dou t as dou f by dou u times dou u by dou t, and plus terms of the order of delta t square, that is coming here, and we represent this dou f by dou u as A, and we can write this dou f by dou u by dou t as u n plus 1 minus u n divided by delta t. So, we are not doing anything here except bringing in the nomenclature of A being equal to dou f by dou u, and this being evaluated u n plus 1 minus u n divided by delta t. And why we are doing that? Because in this case we are getting dou f by dou x like this, we are getting a derivative. So, this will become dou by dou x of u n plus 1 minus dou by dou x of u n like that. So, finally, f n plus 1 is being evaluated as dou f f n plus A times u n plus 1 minus u n, and this approximation is also second order accurate. So, when you look at this, terms coming from this approximation are second order accurate in time, and these things are also being approximated in a second order accurate kind of thing here. So, it is not over yet. So, in order to account for this, I think it is just the same thing, I forgot to delete that. So, we have Fn like this, and therefore now we can write dou f by dou x at n plus 1 as dou f by dou x at n plus dou by dou x times a times u n plus 1 minus u n. And why is that? So we differentiate this with respect to x. So you get dou f by dou x at n plus 1 equal to dou f by dou x at n plus dou by dou x of this whole thing, and that is what we have here. And we can make use of this expression here to write this as ui n plus 1 minus ui n divided by delta t equal to minus half dou f by dou x at I n plus dou f by dou x at I comma n, which is coming from here, plus dou by dou x of a times u I plus I n plus 1 minus u I n by delta t plus delta t square. Okay. So now we have this dou f by dou x here at I n and these kind of things, and you have dou by dou x here. These things are evaluated using central differences, so that we can have second order accuracy in space. So once we do that, we can write this as ui n plus 1 equal to ui n times delta t here, and f I plus 1 minus f I minus 1 by 2 delta x is coming from here, and you have this plus this 2 and this 2 will cancel out to give you this. Okay. So and this term is being evaluated as, again you have the minus delta t that is coming from here, and you can write this as a I plus 1 n times u I plus 1 n plus 1 minus a I minus 1 u I minus 1 n plus 1 by 2 delta x. Now what are we doing here? We are evaluating dou by dou x of this quantity here, and this a here is a function of u. It is dou f by dou u, it can be a function of u here, and we are evaluating this a at nth time step. Okay, so that this can be evaluated, and we are evaluating this whole thing using central differences. So we are writing this as a I plus 1 here, u I plus 1, and we are writing for this one a u I n, a I minus 1 and u I minus 1 here. But out of this, these two terms both are functions of u. A is being evaluated at n and u is being evaluated at n plus 1. So this is I think this is n here. So this is written as this plus a I plus 1 n, u I plus 1 n, and a I minus 1 n and u I minus 1 n. So you can see that this quantity here is being evaluated as half of u's being evaluated at n plus 1 and u's being evaluated at n. Okay. And so that you are essentially getting n plus 1 and n average here. Okay. And we also have the a's always being evaluated at n, and spatially u's are being evaluated in such a way that there is central differencing, I plus 1 and I minus 1 and I plus 1 and I minus 1. So together this gives us an approximation for the ui n plus 1 evaluation. So if you look at this expression here, what do we need in order to get ui n plus 1? We know ui n f I plus 1 n, and so this is at nth step, so this can be evaluated explicitly, and here a I plus 1 n, so explicit evaluation. Here you have u I plus 1 n plus 1, so this we do not know, and you have u I minus 1 n plus 1, this also not known because this is at n plus 1 time step, and here you have I plus 1 n n, so this is known here, this is known, this is known. So in the whole expression here, in order to get ui n plus 1, you also need to know ui plus 1 n plus 1 and ui minus 1 n plus 1. So, together you have the equation here involves ui I n plus 1 as a function of ui plus 1 n plus 1 and ui minus 1 n plus 1. So, in 1D case this gives us a tridiagonal matrix involving ui, ui plus 1 and ui minus 1, and you can write this as a tridiagonal matrix and then we need to solve it. So, to that extent this is an implicit formulation. Okay. So, when we look at the beam warming method for the solution of this equation here, we have derived a second order accurate in time expression of delta t square through manipulation, and we finally brought it as dou f by dou x and all these things here, and we have accounted for nonlinearity here, and these spatial derivatives here and here are evaluated using central differences throughout so as to make it second order accurate in time in space. So, second order accurate in time, second order accurate in space, and implicit because ui n plus 1 requires ui plus 1 n plus 1 and ui minus 1 n plus 1, and other terms which are involving the values at nth time step. And finally, this is linearized because this ui n plus 1 has this a here, this a involves u. So, this is where the nonlinearity is coming, but we have avoided the nonlinearity by evaluating this coefficient a at nth time step. So, this is known as the Picard substitution. The nonlinear coefficient is evaluated using the old value and the actual variable value is evaluated using at the current time step. So, part of this nonlinearity is eliminated by making this coefficient based on the previous time step value. So, this particular overall scheme here is implicit, it is second order accurate in both time and space, and it is linear, and it gives us, in this case of one dimensional calculation, it gives us a tridiagonal matrix equation, and people have efficient methods for the solution of tridiagonal matrix methods. So, that is the advantage of the beam warming method. So, in the next lecture we will see how this is actually used, can be used for the solution of our coupled equations, these equations, because these are the ones that need to be solved in the real case. It is not just a simple one equation, but we can see how the method has come about. So, we can see how we have put together, how the method of beam warming method has been put together to solve this equation by incorporating special features, the features that we would like to have. And what are those features here? When you finally get the prescription, the final prescription, we have ui n plus 1 being evaluated using a method which is second order accurate in time, second order accurate in space. So, that means that we have good accuracy, and something that is linearized, it is f is a nonlinear term, it is linearized by having the coefficient here evaluated at nth time, the previous time step value. So, through the Picard substitution process this has been linearized, and finally we have a desirable form of the implicit scheme. And what is the desirable form? It is a tridiagonal form. Tridiagonal form, as we will see in module 5 in the next module, is a desirable form of a matrix equation for which efficient methods are known. And so, that means that we can solve the equations efficiently very quickly without requiring too much of memory and without requiring too much of computational time. So, it incorporates all these features, and what we have seen now is the case for a 1D for one dimensional flow case, and also for a single equation dou u by dou t plus dou f by dou x equal to 0, and we will see how this whole thing is packaged together to solve all the equations, that is the Navier-Stokes equation plus the energy equation for compressible flow in the next lecture.